So now we're going to go on to having a look at a group of hypothesis tests where we're having to have a look at the means of two different populations. So we're going to start off with small sample, known population standard deviation, and large sample, known and unknown standard deviation. Now hopefully this sounds familiar because we've already talked about this twice so far. If you remember back at the beginning of this year, we had a look at this table here linked to confidence intervals, and we talked about what separated normal and T, and we said that it was a large sample with a known population standard deviation or an unknown population standard deviation. And remember, the reason behind that was that because the sample is sufficiently large, the sample standard deviation is going to be approximately the same as the population standard deviation, and small sample, known population standard deviation, all fell under the category of using the normal distribution or Z distribution. And the other category that we had, which was small sample size, unknown population standard deviation, was separate. We said that for that one, we had to use the T confidence intervals. Not only that, but we talked about this again. The yellow ones here, the normal ones, they're hypothesis tests for a single sample of data. We covered that in AS. We've already had a look in A2 at how we do the hypothesis test with a single sample of data where we have a small sample and an unknown population standard deviation when we had a look at the single sample t-test. Now, we are moving on to having a look at when we have two samples of data. And like I said, this first one here, our small sample known population standard deviation and large sample known and unknown standard deviation, is our normal. And that is because of the reasons why I've just mentioned. So we know from last year that central limit theorem that the average of a sample size n taken from a normally distributed with a mean mu x and a standard deviation and a variance of sigma x squared, and a sample of size m taken from a normal distribution of mu y with a variance of mu y squared. So there we're just describing two distributions that we have then written up here. So we know that the means of the first sample would follow the normal distribution still, with a mean of the same and a standard deviation of the standard deviation over the square root of m. But here they've talked about the variance, so because we've squared the top, we've squared the bottom, so we've got sigma x squared over n. And the mean of the y sample is going to be with a mean of mu y and a variance of sigma y squared over m. So if we consider the distribution of x bar minus y bar, or y bar minus x bar, we can do this testing two different population means. So we're looking at the difference of the two population means. For these hypothesis tests, there are different ways of writing this. We're going to write our h naught as mu x equals mu y. And we're going to write our h1 as mu x is more than or less than mu y, or mu x is not equal to mu y for our two-tailed tests. As we talked about when we were looking at the Wilcoxon rank sum test last year, because we have two different means that we are using in our hypothesis this time, we need to define both of them very carefully. The reason for this is even if your subscript makes it very clear which category each one is referring to, we still need to make that clear to whoever is reading it. So it might be clear to you, but we need to make sure it's very much stated in our working what each of the mu's, what each of the means is signifying. So these hypothesis tests that we're going to look at, they're a little bit different for these first two. The normal one, our test statistic, we're going to get by using this formula here. Now there is a version of this in the formula booklet. This is on page 6 in the formula booklet. However, the version in the formula booklet is this one. So this is the one that you should see on page 6. And this is the formula that we're using. We just use a simplified version of it, which means that you need to remember that if you are looking this formula up from your formula tables, we don't actually end up using this bit in our formula. So as I was saying, which has a version given in the formula booklet. This formula is for the Z values for the test. And because this gives us the Z value, that means that we are going to have to compare that with a Z value. So for the critical value, so remember that this here is going to give us the Z value. And because we need to compare that to another Z value, we're going to get our critical values by using the inverse normal function so we can compare this to our Z value. And if the test statistic is bigger than the critical value, this time, that is when we're going to reject H0, because it's similar to the t-test in the fact that we are wanting it to be more than that value in order to compare it, or the size of that value to be more than our critical value in order to say that we've made a difference. If our test statistic is smaller than the critical value, we're going to end up accepting H0. As a normal distribution and t-test with single samples, if you are assigning letters, then you must define them. So I've already talked about that. For instance, you have to say that mu A is the population mean of group A. So we're going to have a look at our example, our first example. So here we have the alkalinity in milligrams per litre of water in the upper reaches of a river in a particular region is known to be normally distributed with a standard deviation of 10. The alkalinity readings in the lower reaches of the river in the same region are also known to be normally distributed with a standard deviation of 25. Alkalinity readings are made in the upper and lower reaches of the river in the region, and the following samples are obtained. So there we have a sample from the upper region and we have a sample from the lower region. Investigate at a 1% significance level the claim that the mean alkalinity in the water in the lower reaches of the river is greater than that in the upper reaches. So to start off with, we are doing H0. We want the mean in the lower reaches to be greater. So we're going to have mu L equals mu U. And our H1 is going to be that mu L is greater than mu U. But we have to define these symbols. So mu L is going to be the population mean alkalinity level in the lower reaches, and mu U is going to be a population mean alkalinity level in the upper reaches. So then it's a good idea to write down a summary of the information that we have. So we have mu L and we have mu U, and we're just going to write down the information that we have about these two. So mu L, we know the alkalinity readings in the lower reaches of the river normally distributed with a standard deviation of 25. So that is our sigma L. It's the population standard deviation that we've been given there, is 25. The standard deviation in the upper reaches was 10, and again that's the population standard deviation. We also, if we have a look at our formula on the previous page, we need to know mu, or x bar, and we need to know n. So we need to know how many pieces of data we've got, and we need to know what the mean of the sample is. So we're going to have XL bar, we're going to have XU bar, we're going to have NL, and we're going to have NU. So the number of pieces of data in the upper reaches is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of pieces of data in the lower reaches is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Just be careful there. Make sure you always actually count the piece of data. It looks like there's only 4 more in this one, but that's because the spacing, if you have a look here, the spacing is off on there. That could happen in the exam, so make sure you're actually counting them. So then we need to go into our normal statistics part of our calculator. We need to type in the data into the first list, just as we have done in AS when we were trying to find the mean of a sample of data, and we looked at this again when we were looking at T. Remember, after you have entered the data into your calculator, always double check it, make sure you haven't made any errors, because after this we're going to get our value from the calculator, and if we've got that wrong we're going to lose marks. Then we're going to calc. We need to check our set. This is correct. We put our variable into list 1. We don't have any frequencies, so we need that just to say a 1. And then we only have one variable, which is the alkalinity level in the upper part of the reaches. So we click on 1 var, and there we go. We've got our mean, which is 80.5. Going to do the same now for the lower part of the reaches. So we've got 86, 95, 135, 121, 68, 64, 113, 108, 79, 62, 143, 108, 121, 85 and 97. And again, just double check that you've entered all of those in correctly. One var, and our mean is 99. Remember as well, you can check your N with this part here. I could have checked it with when I put my U's in as well, but this screen does also tell you how many pieces of data you have. So this one had 15, so I know that I've definitely counted those correctly. So then we're going to use our formula. So remember that this gives us Z, which is our test statistic, and we have to do mu L, which is 99, minus mu U, which is 80.5, divided by the square root of 25 squared over 15 plus 10 squared over 10. And now we just need to enter that into the normal part of our calculator. So 99 minus 80.5 divided by the square root, shift and then the squared sign, of 25 squared over 15 plus 10 squared over 10. And that gives us 2.57 as our test statistic to 3 significant figures. Remember, you can give it to more than 3 significant figures, but don't give it to less than 3 significant figures. If you would have decided to do your takeaway in the other way around on the top, then you would have ended up with this as a negative. Remember to use your modulus lines to make this into a positive. So then for our critical value, we're going to use our graphical calculator in the stats function again. We're going to go into dist norm, inverse norm. This is a one-tail test. So if you always make it so that your tail is going to the right, then you just have to think of it as we do with a normal hypothesis test. So if it's a one-tailed test, as long as you've already got the tail going to the right, our critical value is either going to be the area of the significance level for a one-tailed test. So it is in this case because it's 1% and it's one-tailed, so we'd just put 0.01. If it was two-tailed, just like we do in a normal hypothesis test, we'd halve the significance level and make that our area instead. So because this is a one-tailed test and it says that we're going to the right, we've got 0.01. And because we're trying to use Z, which is the standard normal distribution, our standard deviation is going to be 1 and our mean is going to be 0. And that gives us our critical value of 2.33. So as I've explained, the reason for this is, if I draw you a quick, very wonky normal distribution curve, we're wanting it to be rare. If you think about the standard normal distribution, our mean is in the middle, which is 0. We have 3 standard deviations. The standard deviation is 1. Within 3 standard deviations of the mean, we should have 99.5% of the data. Here, our test statistic is 2.57. Our critical value, though, was here at 2.33. So you can see that it's further away from our 0. It's more of a difference, which means that we are going to be rejecting H0. So I'm not going to do that every time. I just did that quick sketch there to show you why this means that we end up rejecting. So as the test statistic is bigger than the critical value, we reject H0. So at a 1% significance level, there is sufficient evidence to suggest the mean alkalinity level in the lower reaches is greater than the upper. Just quickly looking back here, it could ask us to state an assumption. Looking at the information that we have here, I'm quickly going to read it to you again. The alkalinity in the water, the upper reaches, is known to have normal distribution, standard deviation 10. Lower reaches, normally distributed, standard deviation 25. We took readings from the upper and the lower parts of the region. The sample obtained is this. But it doesn't have the key word there saying that this is a random sample. So we could state here that we are assuming, so our assumption is that the samples are random samples of the lower and upper reaches. And remember that is important. We talked about that in normal hypothesis testing with a single sample and t-hypothesis testing with a single sample. And even in confidence intervals, whether it's a large sample or a small sample, it always has to be a random sample that we are taking. So moving on to have a look at our second example. So here, looks very similar, doesn't it? We've got the alkalinity in milligrams per litre of water in the upper reaches of a particular region is normally distributed with a standard deviation of 10. Alkalinity reaches in the standard deviation of 25. Alkalinity readings are made in the upper and lower reaches, and we have this sample as follows. Again, we are assuming the samples are random samples of the upper and lower reaches. Got our data here again. If you have a quick look, because this is going to save me a bit of time. Oh look, the data is exactly the same as before. Looks like I put the same question twice, but if we carry on reading, investigate at a 1% significance level the claim that the mean alkalinity in the lower reaches of the river is more than 10 millilitres more than the upper reaches. Now you have to read these carefully. These come up quite a lot where they'll give you a value that is more than it. And the reason why you have to be careful is because if it just said is 10 milligrams per litre more, then that's a two-tailed test. Either it is 10 milligrams per litre more, or it's not 10 milligrams per litre more. But this, it says more than 10 milligrams per litre more, which means that this is still a one-tailed test. So our H0 would be that mu L, keep it the same way around as I did before. Mu L equals mu U still. And our H1 would be that mu L and the plus 10 has to go on our smaller one, and it has to be in both of our hypothesis tests. So we're saying that the lower is 10 more. So that means that if I added 10 onto my upper reaches, it would still be smaller than my lower reaches. That is what this is saying. And this takes quite a lot of practice to get down. If we always remember that we're adding whatever the value is onto the smaller one, like we have here, it does make it a little bit more simple. And again, you have to define those. So mu L is the population mean alkalinity level in the lower reaches, and mu U is the population mean alkalinity level in the upper reaches. I know it's boring to do. Look, I've just done it twice, okay? Do it every time. You will get used to it, and then you'll remember to do it in the actual exam. So again, if we write down a summary of what we know about both of them. So again, we already know that sigma L is, so lower was 25. Sigma U is 10. Number of pieces of data in the lower is 15. Number of pieces of data in the upper was 10. Mean in the lower was 99. And mean in the upper was 80.5. Yes, 80.5. All of that is the same. However, this time, when we're trying to find our test statistic, our Z, the top part of our fraction is going to be slightly different. Now, the way that I like to think about it is, if I was to try and take this to one side here, I would move and try and keep it positive, because that just makes it a lot easier. I would have to move my mu U plus 10 to the other side, which means that I would have the sample mean of L minus, because it's positive on this side, when I take it to the other side it's going to be negative, in a bracket, mu U plus 10. Because I put it in a bracket, I've got a plus. If I didn't have the bracket there, I'd have to have a minus. The bottom of our fraction, however, stays the same. So divided by the square root of sigma L squared over NL plus sigma U squared over 10. So I just realised I've written something wrong there. There we go. So then we have to put in those numbers at the top. So that means that we're actually going to be doing 99 minus 80.5 plus 10, bracket is very important, divided by the square root of 25 squared over 15 plus 10 squared over 10. And now we can put this in our calculator. So fraction, 99 minus bracket 80.5 minus 10, plus 10, divided by the square root of 25 squared over 15 cross plus 10 squared divided by 10. So that has given me a test statistic of 1.18. Again, it's very important that you clearly label that as your test statistic. My critical value, I'm still going to have to use my inverse normal. So dist, norm, inverse normal. Remember to always have the tail going to the right. This is still a one-tail test, so we don't have the significance level, so the area is still 0.01. We're still trying to compare it to a z value, so we still need the standard deviation as 1 and the mean as 0. And that gives us 2.33. So this time, our t is smaller than our critical value, so that means that we're going to end up accepting H0. So as the test statistic is smaller than the critical value, we accept H0 at a 1% significance level. There is insufficient evidence to suggest the mean alkalinity level in the lower reaches is 10 milligrams per litre more is, sorry, I've missed a more right there. Sorry, is more than 10 milligrams per litre more, that should say. Than, missed a more right again. Than in the upper reaches. And that word in there is very important, okay? You need to make sure that you've written that correctly. So is more than 10 milligrams per litre more than in the upper reaches. It's quite a mouthful, but you need to make sure you definitely got that there. So now, as I've just said, if it's a small sample, like we had then we need it to be normally distributed. And in both of those situations, because the background information that we had was the same, it did clearly state that it was normally distributed and we did have a small sample. Remember as well that it always has to be a random sample, and sometimes you might have to write that as an assumption if it's not clearly stated in the question. So now I'd like you to pause the video and give the 2 Now You Try questions a go. So hopefully you paused the video and you gave the first Now You Try question a go. So this time we've got scientists carry out a study in a particular species of snake. Amongst other things, this involved investigating the lengths of adult specimens. It is known that the lengths are normally distributed, with the standard deviation being 7 centimetres for males and 8.5 centimetres for females. The scientists have a theory that on average the male snakes are 3 centimetres longer than the female snakes. So this is a two-tailed test because it's strictly 3 centimetres longer. So they want the males to be 3 centimetres longer or not 3 centimetres longer. So that's why it's a two-tailed test. As I said before, we're adding whatever the length is onto our smaller one. So this time the smaller one was going to be the females. So as you can see here, I've got mu F plus 3, and we're saying that's equal to or not equal to mu M. They trapped 9 adult male snakes and 11 adult female snakes. Here's our lengths, and we're having a look at the scientist theory at a 10% significance level. So again, you need to define what symbols you've used and what they mean. So mu M is the population mean length of male snakes, and mu F is the population mean length of female snakes. You could have put of this species because it's only a particular species we're talking about. Again, summarising what we have, so we've got from the information at the top that the population standard deviation of the length of male snakes is 7 centimetres, the population standard deviation of the lengths of female snakes is 8.5 centimetres. We've got 9 males in our sample, we've got 11 females in our sample, and then I have put both of those in my calculator, one after the other, and got the 2 corresponding means. Then to find the Z value, our test statistic, we have to use the formula, so that's going to be if you think about how you would rearrange this, we'd have 66.7 minus the female plus 3, so minus 87.2 plus 3, divided by the square root of 7 squared over 9 plus 8.5 squared over 11. When we put that in our calculator, we get a test statistic of 1.88 to 3 significant figures. As you can still see it here in my calculator, 1.8754019996. For the critical value this time, we need to go into dist, norm, inverse normal. This time, remember the tail needs to be going to the right, but this is a two-tailed test. So the significance level is 10%, but because it's two-tailed, we have to half that to give us 5%, so 0.05. Standard deviation is still 1, mean is still 0, and that gives us our critical value of 1.64 to 3 significant figures. So as the test statistic is bigger than the critical value, we're going to reject H0. Our 10% significance level, there is sufficient evidence to suggest that the mean length of male snakes is 3 centimetres longer than female snakes. And again, you can see here at the bottom that I've added the assumption again because it didn't say anything about those snakes being a random sample. It just said that they trapped 9 males and 11 females. It didn't mention that these were a random sample of the populations of male and female snakes of this specific species. So that is the assumption that we are making, that they are a random sample. So again, I'd like you to pause the video and give the second now you try question a go. Okay, so hopefully you paused the video and gave the now you try question a go. So here we have, after this year's examination, there is thought to be a difference between the performance of students in 2 psychology modules, A and B. Many of this year's students commented that they thought that module B was much harder. A random sample of scripts from module A and B produced the following results. So this time it has told us that we had a random sample. Test at a 5% significance level if there is a difference between the performance of the students in the 2 modules. So even though here it says that that pupils thought that B was harder, what we're actually testing for is a difference. So you need to be careful with this in questions. Make sure you double check what it is that you're actually testing, not just going off the first thing that you read and then running ahead with the test. So that means that we're testing our H0 is that mu A equals mu B, our H1 is that mu A is not equal to mu B. And you can see again, I've defined them. It doesn't say if these are marks or percentages. I went for marks, but they may be percentages because it could just be that one test is out of more than the other. But I put the population mean mark on module A, the population mean mark on module B. You can see again, I haven't summarised this time because they've given us a summary at the top, and they will do this if you have a large sample because they don't want you spending ages trying to figure out the mean of a large sample. So then we've got 52 minus 48 divided by the square root of 20 squared over 100 plus 20 squared over 150, which gives us a test statistic of 1.55. Again, we have a two-tailed test, so make sure it says right, half your significance level, standard deviation of 1, mean of 0, which gives us a critical value of 1.96, which means as the test statistic is smaller than the critical value, we accept H0. At a 5% significance level, there is insufficient evidence to suggest that the mean mark on test A is different from test B. So remember to be careful. Do I need to make any assumptions this time? Well, it does say the random sample one. And because both of my samples are sufficiently large, I don't need to have anywhere that they should be normally distributed, so that's fine. Always check the size of the sample. If it's a small sample, then somewhere it has to say that they were normally distributed. If it's a large sample, then we only need to have the random sample. But if it's a small sample, you still need for it to say that it's a random sample. Thank you very much for listening.